Welcome back to this tutorial. In this video, we can discuss about next form of normalization. That is about this Boyce called normal form. We can also call it as the Bcnf. Okay. So before starting the discussion about this Bcnf, we can just revise the factors regarding the previous normal forms. Okay. So in the first normal form, the attribute must be atomic. Okay, and the second normal form, what are the condition for a relation to be in second normal form? The relation must be in first normal form, and every non-prime attributes are fully functionally dependent on any of the candidate keys of the relation. Okay, so this second condition actually used for removing redundancies due to dependencies like this. A prime attribute derives a non-prime attribute. So these second conditions focused on these type of dependencies present in the given relation and tried to avoid the redundancies due to this type of dependencies. Prime attribute derives non-prime attribute. Right? So the third normal form. Conditions are like this. The relation must be in second normal form first. Then non-prime attribute should not be transitively dependent on candidate keys. This is the second condition. In another way, we can define the second condition like this. If a relation is in third normal form, then there should not be any dependency like non-prime attribute derives another non-prime attribute. That means the third normal form focusing on dependencies like this in the given relation. Non-prime attribute derives non-prime attribute. And this third normal form tried to remove the redundancies due to this type of dependencies present in the relation. Okay, we have some more possibilities for the dependencies like this. We have dependencies like this in the given relation. Prime or non-prime attribute derives another prime attribute. In the previous cases, RHS is always non-prime attribute. But we have one more possibility like this. Prime or non-prime attribute derives another prime attribute. The presence of this type of dependencies that may generate redundancies in your relation. So our next type of normal form, that is Bcnf, focusing on this type of dependency and try to remove the redundancies due to this type of dependencies. Okay, now we can consider the condition for a relation to be in Bcnf. Okay, so Boyce called normal form, we can call it as Bcnf or 3.5 NF. This is not the fourth normal form. This is 3.5 normal form because this is the stronger version of our third normal form. Just a modification over the third normal form in order to make it more stronger. Right? So that is why it is calling 3.5 normal form. Okay, so these are the condition for a relation to be in Boyce chord normal form. It should be in third normal form. Then for any dependency x implies y, x must be a super key. Keep this point, for any dependency x implies y. This is the general syntax. An attribute or a set of attribute deriving another attribute set. But the LHS part must be always the super case. Okay, so consider some examples. Here we have a student relation with attribute student ID, course and tutor ID. Right, that the meaning is the student with ID 101 is joined for a course COA. That subject is handling by a tutor with ID T1. Another student with 102 joined for CP, C programming course. That subject is handled by the tutor with ID T2. This 102, the student is also joined for the COA course, but the course is handled by another tutor here with ID T4. For 101, the COA course is handled by tutor T1. And for 103, as joined for dbms course, which is handled by the tutor with ID T3. And this 103 again joined for COA course. And his or her course is handled by the tutor with ID T1. Okay, so from this it is clear that a tutor for a single course we have more than one tutors, and also the student can join for more than one courses. Okay, so from this given relation it is clear that using the SID value alone we can't uniquely identify each of these rows in the relation, because each and every student can join any number of courses. In this, the course student with ID 102 is joined for two different courses. Again, student with ID 103 joined for two different courses. So it is clear that using this student ID value alone, we can't uniquely identify different courses. Different tuples of this relation. So instead using SID alone, we need to use a combination SID and course as the candidate key here. Using this combination, we can uniquely identify each of these rows here. Now consider certain valid dependencies over this relation. SID and course can uniquely identify tutor ID. Is it right? If this SID and course values like this 101 COA, this pointing to one and only one tutor ID T1. And if you are given with SID 102 and course CP, this particular information pointing uniquely to this ID T2. And if you are given with 102 COA, this particular combination only pointing to this particular tutor T4. So this one uniquely derive the tutor value. So this is a valid dependency over this given relation. Now consider this. Tutor derives course. That means if you are given with the tutor information, we can uniquely identify the course which is handled by that particular tutor. If this tutor ID is given as T1, T1 pointing only to COA. Here and here. This is a valid dependency. And again, if you are given with tutor ID as T2, which one is pointing to course CP only. T3 pointing to dbms only. And T4 pointing to COA. So this dependency is again a valid dependency over this given relation. Okay, so this given relation is in third normal form, because here all the attributes are atomic, and here using this dependency it is clear that there exists no partial dependency, because SID and course are the prime attribute. There exists no partial dependency with this prime attribute with any of the non-prime attributes. So this relation is in second normal form. There exists no transitive dependency, or a non-prime attribute derives non-prime attribute. Such dependency is not present here. Non-prime attribute derives non-prime attribute. Such dependency is not available here. So this relation is again in third normal form. Right. So our first condition for BCNF is satisfied. Relation is in third normal form. Now we want to check whether this relation is in BCNF. If it is not in BCNF, we need to decompose this relation in order to make it in BCNF. Okay, so consider the condition for a relation to be in BCNF. For all the dependencies like X implies Y, the LHS part must be a super key. Right? So consider this dependency first. SID, course derives tutor information. So this one is a valid case. This one satisfies the condition for the relation to be in BCNF, because SID course is actually our candidate key. All the candidate keys are super keys. Right? So this one satisfies the condition for this relation to be in Bcnf. Now consider the second one. Tutor derives course. Is this tutor is a super key? No, tutor is not a super key because tutor can't alone uniquely identify each of these records uniquely. So this tutor is not a candidate key and not a super key. Right? So this one violates the condition for the relation to be in Bcnf. We want to decompose now. Okay, so we can decompose and make two child child relations like this. This one violate the condition for Bcnf. So make these two together and form a relation like this. Tutor and course. And this tutor act as the primary key. Using this tutor information, we can uniquely identify different course information. Right? And this is the second relation. Here we can consider all other attributes. Without forming any invalid dependency, we can collect all the attributes together in this relation. Okay, so here we have SID and tutor attribute. Why this tutor attribute is selected instead of our course attribute? If we choose course attribute here instead of this tutor, what happened? We can make a relation using this course attribute. Using this course attribute, we can define a relation from this table to this table. But the problem is, using the course value, we can't uniquely identify each of these rows here. Because the dependency is like this. If you are given with the tutor information, you can uniquely identify different course value. But if you are given with the course information, we can't uniquely identify corresponding tutor information. Consider this example. T1 is handling COA as well as T4 is handling the same course COA. Okay, if you are given with the course information COA, we can't uniquely identify whether it is handling by this tutor with ID T1 or T4. Okay, so must include this tutor as the other attribute here in this table, because using this tutor attribute we can define a relation with this table here, and using this corresponding tutor value we can uniquely identify different records of this other table. Okay, so must include tutor attribute instead of this course attribute. Okay, so consider one more change here. Here, this particular dependency is preserved here in this table, but this one is preserved anywhere in this table. Okay, so this is the case of Bcnf. Up to third normal form, we have preserved all the given dependencies in the child relations. But here in this case of Bcnf, this is not always possible to preserve the given given dependencies in the child relations. Okay, after decomposition, we can't always preserve this given dependencies. This one is actually preserved here, but this is not preserved in this children. Okay, up to third normal form, all the dependencies that are given are always preserved somewhere in the children after decomposition. But in Bcnf, this is not always possible. Certain dependencies may preserve here in this children, but some are not preserved. Okay, so consider one more example. Relation XYZ. Relation R with attribute XYZ. Valid dependencies like XY derive Z, Z derives Y. Okay, from this we can find out the candidate keys. The relation is already in third normal form and the candidate keys are XY and XZ. Now we want to check whether this relation is in Bcnf or not. For a relation to be in Bcnf, the LHS part of all the dependencies must be super keys. Okay, so consider the first one. xy derive z. xy is a candidate key directly. All candidate keys are always super key. So this one is valid for Bcnf. But consider the other dependency. Z derives y. But this Z is not a super key here. So this one violates the condition for this relation to be in Bcnf. We need to decompose it like this. This one violates the condition, so make these two together in a child relation. Okay, if we know the value of Z, we can uniquely identify different y values. And in the other relation, we need to collect all other attributes of the relation without violating the Bcnf condition. So here all other attributes x and all other attributes are actually x. And instead of for this particular position we have two possibilities, z or y. Okay, this z or y is actually used here in order to make a relation between these two tables r1 and r2. Using this z value we can uniquely identify each and every y values from these tables. Suppose if you are using y attribute value instead of this z here, what happened now? In that case, using this y value, we can define a relation between this r2 and r1 because y also present here. Okay, and using that value, is it possible to uniquely identify different records over this relation r1? This is not possible because the dependency is like this. Z derives different y values uniquely. Okay, so in this relation R2, along with this x, we need to keep this z attribute so that using this z, we can make relation over this R1. And this set actually acts as the primary key of this R1. So this set is the foreign key here. Using this foreign key, we can generate a relation or we can define a relation with this R1, and using this set value, we can uniquely identify different y values. Okay, so this is a property about the Bcnf. Okay, thank you.